lecture, I will explain the introduction of DC motor. In the introduction lecture, we discussed what is a machine which converts one form to another form, either electrical to mechanical or mechanical to electrical. A machine which converts a machine which converts electrical input to mechanical output, then we can say that the machine is called as a motor. A motor which converts electrical input to mechanical output. So now, what is the principle of operation of DC motor? So if we draw the diagram, this is a field winding is wounded on the field poles and excited with an external source. That too is a DC. Then it acts as a north pole and another one acts as a south pole. Whenever current carrying conductor placed in a uniform magnetic field, it will experience a safe force. That is the principle of operation of DC motor. Whenever current carrying conductor placed in a uniform magnetic field or a steady magnetic field, or steady magnetic field is produced by the DC supply, uniform magnetic field, it will experiences a force. The magnitude of the force is according to Lorentz force equation, and the direction of force is decided by Fleming's left hand rule. Stretch the three fingers. One is perpendicular to another. If forefinger represents direction of magnetic field, and middle finger represents direction of current, thumb indicates direction of force. Here the force is the unknown quantity. Here I am taking the singleton machine. So this is our commutator. The conductor AB is fixed to the commutator segment X. The conductor CD is fixed to the commutator segment Y. So this is our commutator, and between these two commutator segments it is separated by mica insulation, and brush B1 is always contact with the conductor which is existing under the north pole. Brush B2 is always in contact with the conductor existing under the south pole. Here I am giving an external supply, that is our voltage. So the current which is flowing like this, so this is P and M of the source terminals. Source has two terminals. P2 brush B1 to the current is enter like this. Conductor A to B, conductor C to D, and brush B2. The current leaves through brush B2 and reaches the M terminal. So whenever current carrying conductor placed in a magnetic field, it will experience a force. I will explain in another way. This is a north pole and south pole. The flux lines are coming from north pole and south pole. If I am taking this single conductor, the front view of the conductor is small circle. If the current is passes through this conductor is into the conductor, so definitely if current flows through a conductor which will produce a magnetic field by applying a right hand grip rule, it is into means obviously it is a clockwise. These are called the flux lines which is produced by the conductor. If these two are interacted, so the flux lines are coming like this. Flux lines are coming from like this. So here it will be downwards. If you observe this, these flux lines are in this direction. Number of flux lines are in this direction, that is produced by the magnetic field. When the flux produced by the conductor is in opposite direction, then both are is cancelled. And at this position, as the flux produced here, see you can draw like this clearly. So this is a flux direction, but the magnetic field which is produced here is also in the same direction. Then here the flux will be aiding. Due to this, the flux produced by the conductor and the flux produced by the magnetic field both are cancelled at this position. Finally, a force will be developed like this. So here the force will be cancelled. Due to this, it is a tendency to rotate the armature conductors. Armature conductors are rotating. So in which direction means by applying a Fleming's left hand rule. See, this is the north pole and south pole, and suppose here conductor is there. The flux lines are coming from north pole to south pole, and the current is into the conductor. The force which is developed here, let's check it. Is it a clockwise or anti-clockwise direction? As the force which is developed here in this direction. The force which is developed here, it is in this direction. Then the conductors are rotating in anti-clockwise direction. By applying a Fleming's left hand rule, we can know the direction. So here also same thing, the conductors are rotating in anti-clockwise direction. After half rotation, the conductor CD comes under the north pole the conductor AB comes under the south pole. So anyway, field winding is present, and that is excited with the DC supply. It will produce a magnetic field. So the brush B1 is always in contact with the conductor which is existing under the north pole. The conductor which is existing under the north pole. The brush B2 is always in contact with the conductor which is existing under the south pole. So the voltage source terminals are P and M. Again, the current is leaves from positive terminal of the supply. The current flows through P and brush B1, and now it is D2C, B2A. After the brush B2 to M. The external terminals are same, but coming to its internal terminals, that is through the conductors, previously is from A to B and C to D. Now it will be D to C and B to A. So whatever the current is there, current is an alternating. Okay. By giving a DC supply also, the current which is flowing through armature conductors is changing. That's why this commutator acts as a mechanical rotating inverter in this case. If you go for a generator, it acts as a mechanical rotating rectifier. Inverter means DC is converted into AC. Again, you can apply the right hand grip rule. So here is the current N2, and the current will be dot. By applying the Fleming's left hand rule, it is from north pole to south pole. Okay, and the current is into the board. Is from north pole to south pole, and this will be downward direction, and this will be upward direction. Then the armature conductors are rotating in anti-clockwise direction. So it will be rotating in same direction. So here we are taking two supplies. One supply is for to produce the magnetic field, and another supply is to produce or to meet our requirement. What is our requirement? Remains the current which is flowing through the armature conductors, which is placed in a uniform magnetic field. It will experience a force. The magnitude of the force is decided by Lorentz force equation, where F is equal to BAL sine theta, where L is the active length of the conductor. B is the magnetic flux density. And theta is the angle position of the coil. And magnetic field. Position of the coil and magnetic field. With this rotation, there is a cutting action will be takes place. The cutting action will be takes place, and EMF is induced in a conductor. See, because of supply voltage, the armature is rotates. With this rotation, armature cuts the conductors, and EMF is induced, and this EMF is called the back EMF or counter EMF. This is very, very important. See, the rotation of the conductors will be downward direction, The magnetic field is from north pole to south pole. You can observe that the middle finger represents the direction of the, so if you can observe the middle finger represents the direction of the current, but you are not using left hand rule, you can use right hand rule for the direction of induced EMF. For the direction of force, you can use Fleming's left hand rule. Thumb indicates the direction of the rotation, and forefinger depends the direction of the flux, and this middle finger represents the direction of the induced EMF is outwards. So here we are getting, here I am getting dot, and here I am getting cross. So this, whatever the induced EMF is there, that induced EMF and the current flowing through the armature conductors, both are is in opposite direction. That's why we can tell that it is called as a counter EMF or back EMF. Due to this EMF is also current will be circulate, the force is developed. So that's why there is a opposition torque is produced. The electromagnetic torque that is produced by the motor, and the load torque is produced by applying a load, mechanical load, by applying a mechanical load. So this EMF is called back EMF or counter EMF. The EMF which is induced in a DC motor, which is opposite to the supply voltage, then this is called the counter EMF. And EB is equal to 5Zn by 60 into P by A. Same formula. If A is equal to P for lap winding and A is equal to 2 for wave winding. And in a generator we can call it as a generated EMF, but in a DC motor we can call it as a back EMF or counter EMF. That is the importance of the EMF. So EB is equal to V minus IA into RA. Whatever the supply voltage is there, supply voltage is to meet the back EMF and to overcome the armature resistance IA RA. Always the supply which is used to meet the back EMF and armature resistance drop. And the current which is flowing through the armature conductors is IA, and the armature resistance is RA, and EB is equal to V minus IA into RA. So V minus IA into RA. Then IA is equal to V minus EB divided by RA. As you are applying load increases, then the speed is decreases. If a speed decreases, then back EMF is also decreases. We got the equation EB is equal to 5Zn by 60 into P by A. Once design is over, number of poles is constant, number of parallel paths is also constant, and number of conductors is constant, and 60 is also constant. EB is directly proportional to N phi. And if the flux is constant, by giving an electrical supply to the field winding, and EB is directly proportional to N, we have to maintain the flux constant. EB is decreases, then the armature current IA increases. So that is the most important of back EMF. So as the speed increases, then back EMF is increases, then IA value should be decreases. The back EMF is acts as a regulating mechanism. The back EMF is acts as a regulating mechanism. So you can apply the Fleming's left hand rule for the direction of the force. So suppose the flux lines are coming from north pole to south pole, and current is into the conductor, and this thumb indicates the direction of the force. So and B is the magnetic flux density. Okay, that is the significance of back EMF. The back EMF is having same polarities of supply voltage, then only the opposition will be occurred. This is a supply voltage, and the current drawn from the supply is called the line current. The current which is flowing through this one is IA. Okay, and if you apply the KVL to this loop, the armature consists of an internal resistance. This is your circuit EV, and this one is RA. The supply voltage is V. The current which is drawn from the supply is line current. The current which is flowing, this one is armature current. Always the current flows from higher potential to lower potential. And if you apply the KVL to this loop, IA into RA plus EB minus V is equal to 0. Then I got this equation, EB equal to V minus IARA, RV equal to EB plus IARA. This is a voltage equation of DC motor. Voltage equation of a DC motor. Okay, so here field winding is excited with an external supply. Definitely the field winding is present, so that we can have a mechanical load here. Previously it is so we can apply a mechanical load on the armature. So one problem, a 220 volts DC motor has an armature resistance of 0.75 ohms. It is drawing an armature current of 30 amperes driving a certain load of 0. Calculate the induced EMF in the motor under this condition. So a 220 volts DC motor means in a given data is giving a supply voltage. As we discussed in the previous lecture, a 220 volts DC generator means they are giving only electrical terms. So a 220 volts DC generator means that is output terms, that is terminal voltage. A 220 volts DC motor means input is electrical for a DC motor. That's why input voltage is 220 volts. And armature resistance is 0.75 ohms. And armature current is 30 amperes. Calculate the induced EMF under EB equal to V minus IARA, 220 minus 30 into 0.75. So that should be equal to 197.5 volts. It's a very easy problem. Okay, in some problems, EB equal to 5Zn by 60 into P by A. E is given, phi is given, and Z is given, speed is given, and then find out the voltage equation or current like that. E equal to EB plus IARA, and instead of finding the IB, yes, instead of finding IB, so how to calculate IA value? So first of all, you should calculate the back EMF IZN by 60 into P by A based on his given data, and substitute the back EMF in that equation. Then you will get the unknown quantities. And the next one is power equation of DC motor. So V is equal to EB plus IA into RA, and multiply with the armature current on left side and right side, EB into IA plus IA square into RA. So V into IA is called the net electrical input to the armature conductors, and IA square RA is called armature copper loss, and EB into IA is called gross mechanical power developed, in the armature or by the armature. So now EB into IA is equal to, I can write it as V into IA minus IA square RA. So this we can say that it is a mechanical power, gross mechanical power, V into IA minus IA square RA. In order to get the maximum power, condition for maximum power is differentiate this PM with respect to variable. In this, V is constant, the supply voltage is constant, RA is also constant, dPm by dIA is equal to 0, and then differentiation of EIA is V minus 2IA RA is equal to 0. Then IA is equal to V divided by 2RA. Substitute in the back EMF equation, EB equal to V minus IA RA. So V minus V by 2RA into RA. So RA will be cancelled. Then the back EMF I got it as V divided by 2. So at half of the supply voltage, if EB is equal to half of the supply voltage, the maximum gross mechanical power is developed. Developed by the armature. So this is very important. EB is equal to V divided by 2. So in the next lecture, we discussed torque equation of a DC motor. Thank you guys.